7.2 discusses properties of rational exponents. Our essential question is how to use properties of rational exponents to evaluate and simplify expressions. We're not really learning much new here. I'm going to be reviewing all of the properties of exponents that we learned last chapter, only now I'm going to be applying it to rational exponents or fraction exponents, okay? All right, so I'm going to make a table here. I'm going to basically have two columns. One column will have the property, and then the other column will have my example of that property. Okay, so this should work. All right, first property. Again, this is just these properties, you've seen them all before. This is a to the m times a to the n. And what you know from that is that you should do what with these exponents if you have like bases? You're going to add them together. Okay, so what happens if I have, for example, 6 to the 1/2 times 6 to the 1/3? Well, hopefully you remember that you cannot add fractions that do not have like denominators. So we need common denominators first, okay? So what's my common denominator going to be? It's going to be 6, right? Both 2 and 3, their least common multiple is 6, which basically means I need to multiply this one by 3 over 3 and this one by 2 over 2. All right, so really what I have then is 6 to the 3/6 times 6 to the 2/6. And when I add those together, I'm going to get, let's see, so like bases, I'm just going to add the fractions or add the exponents. And really when we're adding, we're just adding the numerators. So that's going to be 6 to the 5/6 power. All right, next property was a power raised to a power. So I went over this quite a bit in the last lesson, but a to the m raised to the n really means that you're going to multiply, right, the two exponents together. So what if I had, as an example, 4 to the 3/2 and I squared that? Well, that's pretty nice of me because that makes this a really easy problem, right? The denominator here reduces with the numerator. And so really all I get is 4 cubed, which is the same thing as 64. So if you wanted to draw lines in here to kind of separate these, that might be useful. All right, next property is going to be, let's see, how about A times B? So I've got some product being raised to a power. Well, that's really the same thing. Now that power gets given to both factors, right? A to the m times b to the m. So for example, 27 to the 1/3 times 6 to the 1/4. And I'm going to raise that to the second power. And now there's a couple of ways that we can go about doing this. I am going to go ahead and just give this to each of these. Okay, so I'm really going to say, well, this is really 27 to the 1/3 squared times 6 to the 1/4 squared. Okay, so this, now I have a power raised to a power. I multiply them, so I get 27 to the 2/3 times 6. Same thing here. I'm going to go to the 2/4, so that's really to the 1/2. Okay. All right, so this is where I'm going to write these as radicals. So I'm going to put them into radical notation so that they make more sense to me. Okay, this is really going to be the cube root of 27, and then I'll square that. Now this reduces to 1/2, right? So this is really going to be the square root of 6, okay, because that reduced to 1/2. Okay, continuing on simplifying, what is the cube root of 27? Well, that's 3. So this is really 3 squared times root 6. Or in other words, 9 root 6. There are no perfect squares under this radical, and there's really nothing else I can do to simplify this. So my final answer here will be 9 root 6. Okay, another property that we just recently reviewed, and we're going to review again, is a to the negative power. So what happens when I have something raised to a negative? It means I take the base and I do the reciprocal of it, okay, and then I raise that to the nth power. But what if there was something already on top? I don't know. There's many ways to do this. I think a better way of thinking about it is like this, right? Because it's only the a that is being raised to that negative n power. Okay. So for example, if you had like 7 here, 7 doesn't go to the bottom. Okay. All right. So let's see what I can give you here. How about we do 25 to the negative 1/2. Well, that's really the same thing as 1 over 25 squared. Or sorry, not squared. Square root. We're rooting because there's a fraction exponent. So the square root. Okay, so simplifying that, I really get 1 over 5. What if we had, let's do one more of those. What if I had, let me think of a good example. What if I had 7 times 4 to the negative 1/2? Notice that the 4 is the only thing that is being raised to a negative. So this would actually become 7 times 1 over 4 to the 1/2. So really that's the same thing as 7 times 1 over the square root of 4. Or in other words, 7 times 1/2. Multiplying straight across, I get 7/2, or 3.5. Okay, so that's another example, because I know you guys get really confused about if you have other things next to the thing with the negative exponent, okay, or other factors, you need to leave that factor where it is, okay, and then this one is the only thing that has the reciprocal being done to it. All right, let's continue. So I'm out of room, so I'm going to go on to the back. Make my 2 columns one more time. Okay, another property that we've learned about in our lives is a to the m over a to the n. So I have like bases being divided. So what I do with the powers then is I subtract them. This is a to the m minus n. Okay, so now let's do that with fraction exponents or rational exponents. So 6 to the 5/2 over 6 to the 1/2. Now let's remember, anytime you're subtracting fractions, you need common denominators. Here I happen to have common denominators, but if you didn't, you'd have to do like what we did on our first example, right? You'd have to get those common denominators. Okay. Well, like bases, I subtract the exponents. Okay, so this is going to be 6 to the 4/2, right? Which really, now that reduces to 6 squared, which is 36. All right, another property that we have. If you have a quotient like a over b raised to the m power. Again, this power gets given to both numerator and denominator. So this is really a to the m over b to the m. Okay, so let's do, how about 8 over 27, the whole thing raised to the 1/3 power. Well, this is really 8 to the 1/3 over 27 to the 1/3, right? That power gets given to both numerator and denominator. Now, I would rewrite this in radical notation. So the denominator determines that this is really the cube root of 8. over the cube root of 27. So now what times itself 3 times will give you 8? 2. What times itself 3 times will give you 27? 3. And we are done. Pretty awesome. Hopefully that was just a nice review as far as the properties go. Now you have to be able to apply them to using rational exponents. Okay, so I've made myself a nice table here that I didn't need the whole paper, so I'm going to do that. Erase that. So let's remember that there are a few things to make simplest form. So there are some things that were important when we were doing simplest form. Exponents are going to be in simplest form when you don't have any more perfect squares or perfect roots underneath the radical. So it's completely simplified. Also, when you have no negatives as your exponents. So no negative exponents, okay? And the last thing, okay, so the last thing is going to be no radicals in the denominator. You cannot have a radical in the denominator. And this is the one that I'm going to focus on right now because I'm hoping that you remember the previous things that I said. So again, no negative exponents, okay, would be simplest form, and no more roots underneath. So for example, if it was the cube root of 8, well, you can take the cube root of 8, right? Because 2 times 2 times 2 gives you 8, okay? So let's focus on what happens if I have a radical in the denominator. We are going to then do a thing called rationalizing the denominator. And it's quite simple to do. Just have to remember to do it. So for example, let's do a couple of these. If I have 1 over root 2, the question is, how can I get rid of that radical in the denominator? Well, that's a square root, right? So if I just multiplied it by another square root, right, don't those undo each other? So now I have root 4, which is really 2 in the denominator, and I'm left with a root 2 in the numerator. And that is totally fine. You can do that. Let's try another one of those. So what if I have, let's say, the cube root of this fraction, 1 over 4. Okay, well, the first thing I would do, a lot of times these are going to be quite confusing. So you can go back and write this in rational notation, okay? So make your exponents fractions. So I would rewrite this as 1/4. Now, I was taking the cube root, so that's what goes in the denominator. So to the 1/3. Now, this is the exact same thing as 1 to the 1/3 over 4 to the 1/3. Okay, and so now we need to think of a way, what can, like up here where I multiplied it by the square root, okay, what can I multiply this by to basically make it so that my exponents are gone? This exponent just becomes 1. Okay, so let's think about that. So what can I multiply this by? It needs to be the same exact base, because if I multiply like bases, I add exponents. So what exponent can I put right here to make this become 1? Hopefully you're thinking to yourself, oh, that's 2/3, because that would give me 4 to the 3/3, which just is 4 to the first power. So I'm going to do the same thing on the top. I'm going to multiply it by 4 to the 2/3. Okay, so really what I end up with then, well, 1 to the 1/3, the cube root of 1 is just 1. Okay, so I get 1 times basically the cube root of 4 squared. Okay, so the cube root of 4 squared, which can't take the cube root of 4. There's nothing times itself 3 times, it'll give you 4. Over, on the bottom, I'm just going to get 4. right? And so now I don't have any more radicals in the denominator. So those are two examples of rationalizing the denominator. If it's a square root, you guys already know that one. That one's pretty easy, right? Okay, this one's a little bit more tricky. So the question is, just multiply it by the same base, raised to a power that when you add the powers together, you get 1. And just for fun, I just want to show you that's why this works. So really this in the denominator was 2 to the 1/2 power times 2 to the 1/2 power. Well, add those, you end up with 2 to the 2/2, or in other words, 2 to the 1st power. Okay, so that's where this comes from, which is pretty awesome. Let's just do a couple more random examples of things that you might see or come across. So another example I'd like to do with you, let's just do a couple more examples. And we're just going to, let's see, I didn't really do any formal examples. So these are just a couple more examples, and the directions are to simplify. Okay, so one of them, what if you have 3x raised to the root 2 plus 1x raised to the root 2? So this is going to throw some of you for a loop, but you just got to remember that anytime you have like terms, they can be added together. They can be combined, right? And this is x to the root 2, x to the root 2. So they have the same exact exponent. So these are x to the same exponent. So these are like terms, and they can just be added together. This is 4x to the root 2. It is simplified. Okay, how about another one? If I have 4 to the 1/4 times 64 to the 1/4. Okay, well, the property that we had for multiplying, let's see here, is the first one we did, right? If I have like bases, I can add my exponents. Notice here I don't have like bases. The question is, can I have like bases? So can I make 64 into something with a base of 4? In fact, 4 cubed is 64. So this is really 4 cubed raised to the 1/4 power. Okay, this is one way of going about doing this. And then I also have 4 to the 1/4 here. Okay, well, let's go ahead and let's simplify this. So I end up with, let's see, 4 to the 1/4 times 4 to the, that will become 3/4. And then if I have like bases, I can add the exponents. So this really becomes 4 to the 4/4, or in other words, 4 to the 1st power, which is just 4. Let's do one more. We're going to simplify. How about x to the 7/5? Okay, so you might be thinking to yourself, well, this is already simplified. What else can I do? I don't have any radicals in the denominator. I don't have any negative exponents. Well, what you do have here is you have 7x's and you're taking the 5th root. So for example, if I told you to take the square root of 64, you would say to yourself, well, that's going to be 8 because I have 2 8s being multiplied and I need to take the square root. So anytime I have 2 8s, I can pull out an 8. Okay, well, the same applies here. I'm really taking, and I'm going to do this 2 ways. I'm taking the 5th root of 7x's. I don't recommend always doing it this way, but just to get used to it, maybe you write it out like this. Okay, so I'm taking the 5th root of 7x's, which tells me that every time that I have 5x's, I can pull 1x out. Okay, so I can pull an x out. Now I'm left with 2 x's, which is like x squared, and those are still going to be under that 5th root. So this could really be either written like that, or it could be written like x to the 5th, or sorry, not x to the 5th, x times x to the 2/5. Either way works. Okay, now another way to think about doing this instead of writing it out this way is to ask yourself, how many times does 5 go into 7? Okay, and it goes in 1 time, right? So that tells me I can pull 1x out. And then how many are left? 2. So then I have 2/5 left. So I'll say that one more time. I can just look at this fraction here and say, how many times does 5 go into 7? It goes in 1 time, so that means I'm going to have 1 x that gets pulled out of the radical. And I have 2 x's that stay under that radical. Okay, I want to do one more example. So what if I give you 4x to the negative 17 fourths? Okay, well, to begin with, we know that 4 doesn't have an exponent, but x does. It has a negative exponent. So it might be helpful to leave the 4 where it is. X to this negative means I need to take the reciprocal of it, which really means I'm going to drop it to the bottom. So now that becomes a positive 17 fourths. So I have a couple of options here. I can do like I just did above, which would be fine, but what's going to happen is I'm going to be left with still another radical in the denominator. So while I have a radical in the denominator, why don't I try and deal with that? So the goal is that I don't end up with any radicals in the denominator. So I need to basically multiply top and bottom by some x to some power that will get me to a multiple of 4. So that way I don't have a fraction anymore. Okay? So what would be a multiple of 4 that is close to 17? Right? So for example, 4 times 1 is 4. 4 times 2 is 8. Right? And so on and so forth. So 4 times 4 gives me 16. But I want it to be a little bit bigger so that way 4 will go in a whole number of times. So that way I don't end up with any more fraction exponents. And then that means I don't have any radicals in the denominator. So what about 4 times 5? 4 times 5 will give me 20. Right? So basically this needs to be x to something that will give me 20 fourths. Well, that's going to be 3 fourths. So I'm going to rationalize the denominator by doing that to top and bottom. So it doesn't always have to be just get it to 1. You can just get it to any whole number. Okay? All right, so multiplying this now, I end up with, let's see, I still have that 4, x to the 3 fourths. And on the denominator now, I get x, let's see, these are like bases, add those, I get x to the 20 fourths. Or in other words, I'll now write it with radicals and I'll simplify this. I get 4. I've got the 4th root of x cubed over x to the 5th. And that would be completely simplified. Oh, I didn't circle my last answer.